All right, so transformations, reflections, inverses, all that fun stuff. All right, so a lot of this is going to be a rehash of Algebra 2. We have covered some of this material ourselves, but we're going to put it all into one big package, tie it with a bow, and call it a day. So, all right, for the function, let's say, we're going to say f of x is the parent function. In fact, well, that's an ugly one. I can say y equals f of x. So y is the independent variable. It's graph this, and f of x is a function of the variable. Now, a parent function is the function without any bells and whistles, without any trappings put on it at all. Some examples of parent functions are x squared, square root of x, the absolute value of x, plain old x. Okay, obviously we could go to x cubed or x to the fourth and whatnot, but these guys don't have any other components to them. They're not being multiplied or added to anything. They're just basically your garden variety examples. So what we're going to play with this thing and see what happens when we add constants, throw in terms, and see what happens. So, for example, and I'm going to go ahead and do some straight ahead examples. Let's use the example of the square root of x. The square root of x, if we were to graph this function, looks like that. We all have seen this graph before, right? Nothing thrilling and exciting yet. But we're going to use this as the example. So if I have f of x plus a constant, let's call it a. All right, this is what's happening is that I'm adding a number to every value on this graph. So the result of happens to this graph when I add 5 to it. For example. Yeah, every point goes up 5 units. This is a vertical shift. You can draw yourself a little picture where now the y-intercept is, instead of being 0, it is moved up a points, a units. If a was negative, it would go down that same value. Now, when I add the constant inside the function itself, so x plus a constant, let's go back to here. This would become, every time I saw an x in the original function, I replaced that with x plus a, whatever the heck a is. All right? So what used to be I've now substituted x with x plus a. Whatever goes inside here, as we've learned in Algebra 1 and all of our previous courses, whatever I plug in for that position in that pair of parentheses gets substituted for every expression of x. So the net effect of this, who can tell me what happens when this, does it shift to the left or to the right? If a is positive. If a is positive, it shifts it to the left. If it's inside the pair of parentheses, as you remember, it does the opposite effect. Okay? All right. Now, if let's play around with some negative signs and see what happens. what happens to this? Flips across x or y? Across the x-axis. Because whatever value you got, you're now plugging a negative sign out in front of it. So if you plugged in 4 into my square root, instead of getting 2, I get a 2, and I slam a negative sign out in front, and it gives me a negative 2, which flips the whole thing upside down. Now, what about this one? Well, let's think about a square root function. Can I plug a negative number into a square root function? With the reals. We're not playing with the complex numbers right now. Can I plug in a negative 4 into my square root of x function? Can I graph that? Good morning, it's Monday. Right. So since this normal parent function does not have a domain of the negative numbers, the only way that this thing could be graphed is if I plug in a negative number into it. For example, what's happening is that I have this. The only way that this survives and actually can give me a value that I can graph is if I plug in a negative number to begin with. So if I plug in negative 3, I get the square root of 3. Okay. So now all of a sudden, it's not the positive number that give me my domain. It has to be my domain. Okay. It only lives in the negative numbers now. So it effectively flips it, this time over the y-axis, because now positive numbers don't work. Only negative numbers work now. All right. Multiply by a constant. Okay. Okay. It's a stretch or a compression horizontally or vertically. No, it doesn't. It only stretches it vertically. It does not compress it horizontally. And we're going to talk about this a little bit. This is a vertical stretch. All right. It goes up a heck of a lot faster than it used to. Okay, so it was the red dot. The red dotted line is now pulled up if a is greater than 1. If a is less than 1, it shrinks it. Okay. Now notice I put greater than 0, because now all of a sudden, if I'm dealing with a negative number, it's going to do what I showed when I put a negative sign out in front of it. It'll flip it upside the axis, across the x-axis. And I have a nice little applet that's going to show that real fast. But I want to go into, actually now is a good time, before I go into the other kinds of stretches. All right, so I made a little graphic. All right, so I have this goofy polynomial not really worried about what its equation is. But this is the, let's call this my parent function for argument's sake, whatever my function is. All right. Now, if you look here, I don't know if, can you guys, it's a little too small. A little better? Okay. All right. I've got this function, and you can see I've got a term 1 out in front, f of 1x plus 0 plus 0. So what I've basically done here is I've created a slider, 4 different constants, for these 4 variables, okay? And what happens when we change these variables. As it is right now, we could simplify that function down to just f of x, okay? But notice one important piece, its roots. The roots didn't change. And that, in a sense, makes sense. Why would the roots not change? Say it again? Okay, algebraically justify that that it wouldn't change its roots. If somebody, yeah. Go ahead, grab the pass. So, in an algebraic sense, why does this not change the roots? What are the roots? How do you get the roots? I'm sorry? Right, but if I actually had the blown up, crazy, whacked out polynomial, right, and I wanted to find its roots, what would I do to it? Okay, so you set it equal to 0 and you pull out a GCF. And then when you divide out that GCF, you're dividing it against 0. So the roots are still the same roots. You're just pulling out a 10 out in front, or a 2, or whatever constant it is that's going out in front of the function itself. Now, take a look at what happens here. What happened? It's a horizontal compression, and what happened to the roots? The roots did change, okay? Because and if you think about what's going on inside the equation, if I had something like this, okay, so if I'm looking at this, and let's say my parent function is that, all right? Now what's happening, if I look at, and if I'm trying to find the roots on this guy, okay, that's what my function would actually look like. Now, let's look at the effect of that 3. If I'm trying to find the roots, I'm going to set it equal to 0. And here, this moment, when you divide out that 3, that you change the root. Because if I didn't have a 3 out there, my root would be -1. But because I'm dealing with this 3 at the end of the process, I'm changing the root. So under normal circumstances, this guy would just look like And let's just do x plus 1. This guy, if I graphed it, what's the x plus 1 do to the whole function? Shift it how? Left, right, up, down, inside out? What does it do? It shifts it to the left. It's the opposite of the normal direction. And it's a double root, right? It has a multiplicity of 2. So that means my graph is going to look like that. But now when I'm dealing, and if I solve this equation, now pull. All right. So when you're dealing with a constant inside the function, it changes the roots because it pulls it in and changes it that way. The effects might look the same, but you can definitely tell by looking at the roots. Okay. Of you who haven't had a chance to play with it yet, I, by the way, have submitted a ticket to get GeoGebra approved on school computers. So hopefully sometime down the road, we'll be able to go to the computer lab and play. But I recommend that you get a moment to try this. I'll be honest with you, this thing took me 15 minutes to put together, maybe 10, okay? And it has all the bells and whistles that I wanted for this lecture. Okay, the sliders functions are awesome. Allows you to insert variables and whatnot. It's really kind of neat. All right. What would happen if I took the absolute value of that function? What would it look like? So what would happen at, say, what looks like -2 here? Hmm? Would it stop and flatten out, or would it do what? It would mirror. Right. Now, let's ask this question. What happens if I just take the absolute value of the x, forget about the function. Every time I plugged in a negative number or a positive number, it reverted to the positive value. What do you think would happen? Let me show you what it does, and then you tell me what's happening. Kind of weird, right? Same now. What's happening? How are the black function and the green function related? Not an inverse per se. Whatever is over which? The y-axis. Whatever is happening on one side of the one side of the y-axis is what's reflected on the other. Because if you think about it, as soon as I plug in a -2 into the green function, it immediately turns that -2 into a +2. So whatever the function's value is at +2 is what it gives it for -2. So it reflects not over the x-axis, but over the y-axis. So let's summarize this. See if we can get a nice set of good notes here. All right. Okay, those are the ones we did a minute before, and now we're going to talk about absolutes. And lack of a good mathematical term, okay, so anything that was negative now flips up to become positive. So this one, instead of flipping over the x-axis, mirroring over the x-axis, it mirrors over the y-axis. Whatever's happening on the right-hand side of the y-axis is what happens on the left-hand side of the y-axis. It effectively, and we see this happen. If you think about this for a second, whenever we did something to the outside of the function, we played around with what happens to the y values. Okay, if I added 3 onto my function, all my y values went up. If I added 3 onto my x inside the parentheses, I played with x and shifted everybody inside and out. So working on the outside of the function affects the y values. Working on the inside of a function plays around with the x values. Okay? Okay. Before we start fooling around with inverses and whatnots, there's an important piece of mathematics that I think is often overlooked, but is very powerful. And it deals with grouping symbols, and we'll if I have this expression, okay? Oh, you're here. Cool. Before I forget, let's try that one more time. There are times when you don't want something outside the pair of parentheses. In a sense, the square root function is a pair of parentheses. It's a grouping symbol. It says, take all stuff and take the square root of it. A nice way wanted to push that 3 into the radical. We're normally dealing with pulling things out of radicals, but every now and a blue moon it's useful to push something in. Effectively, you can do like this. And then, remember what this is really saying is, all right, now I can't distribute that 3 onto the x and the 1, because powers have to be applied before multiplication does. Order of operations still applies. So since there's an exponent in play here, I can't go lower on the food chain. I got to deal with the exponent first. So in order for me to show that, I turn this into and now since they both have the same power, I can play with the bases, because what I'm doing now is this. The step that is all too often forgotten about. Okay, with the square root, it's quite straightforward. With other things, you can pull them too, and you can play with other grouping symbols. For example, okay, if I wanted to push that 3 in, now this is important because if that 3 on the outside was a negative 3, when it gets squished inside the grouping symbol, the properties of the grouping symbol have to be applied. Now this is said about going in reverse. If you want, I mean, get talked about, I'm afraid to constants and absolute value, but you can. We not done? Sorry. Absolutely. Because what's happening, when you go backwards and you pull that out, for example, this, matter yet. Let's just take a break for a second on this. So pulling it back out gives you, in order for you to extract it out, pluck it off of the tree, it has to take with it whatever grouping symbol was given to it in the first place. Here's a good example. Let's pull this out. Do we all agree with that? If I distributed that -1, I just get back where I started. So all I've done is factor out a negative sign, okay? Look at where you end. It's that pulling that constant out. When that constant leaves that grouping symbol, it takes that grouping symbol with it. And that's an important rule because it allows you to pull things out and simplify things. Now, what would happen if that was not a square, but instead a cube? Would it matter? Now, what's negative? Still 1. Okay, so I want you to know that this is a feature of algebra that allows you to push things into grouping symbols and pull things out of grouping symbols. Okay, and every now and then you have to do it in order to make things fly. Okay, so keep this tool in your toolbox because it comes in very often. Yes. Yeah, what about it? Yeah, let's blow it up. One times 1, 1 times -x, -x times 1, -x times -x. Right. But again, that's useful because sometimes what you want, sometimes you're given x minus a, and what you really want is a minus x, pull out a -1. Okay, so you can flip the order of a binomial by just plopping a negative sign out in front of it. Again, another very useful tool, especially if you need to cancel terms out, right? So, for example, the very simple expression that, well, I can't cancel right away, although they look kind of like each other. What can we do? Okay, let's flip the denominator. And now things cancel. All right. So be aware of this and keep it in your toolbox, because I use this a lot. I mean, not in the making of work for you, but in the problems, in the solving of problems from time to time. You need to just turn something around. Turning it around is effectively putting a -1 out in front. Because when it pulls out that absolute value, right, and it pulls out that constant, it's saying take the absolute value of whatever constant you just pulled out. All right. Actually, those. Well, they are. Let's do this. All right. And for lack of doing it on a graph, I'll do it in a table. Okay. Plug in -3 into that equation gives me what? 2. -2 gives me -1. 1. What plugging in 1 gives me? Now back to here. -3 plugged in gives me they're the same graph. Sure. Okay. Now, all right. F inverse. Okay, we've played this before. This is effectively so what was the dotted red line is now the solid blue line. I'm flipping it over y equals x. Okay. Here's some important features of the inverse. Assuming that the inverse even exists, for crying out loud, because it doesn't have to. And I'm not just saying that for some special function or anything in particular. if it's an inverse, if I plug one into the other, I get back x. Let's prove that. Or rather, let's show that. So we know how to take an inverse. We've done it before. You swap the x and the y, and you solve for y. So that's my inverse. Okay. Wonderful, hunky-dory, everybody's happy. Now, let's check my two statements. We'll check this first. That's saying take my original function, jam it into your inverse, you had better get x. So, that's saying so starting with my exterior, I then insert my function. All right. So I've taken the smaller piece, which was the original function of f, and jammed it into f inverse. And now if I go ahead and do some algebra here, the square and the square root cancel. Now what's going to happen with this positive and negative now? Think about it. What happens to that positive and that negative? Ooh. Why did we have the plus or minus to begin? Because the square root function is not a function by itself, right? No. Yeah. So the square root cancel each other out. Now, the negative case is effectively dead, if you think about it, right? Because the square and the square root cancel each other. And now what we really have to deal with is the positive case. Which gave x out. So there is evidence that these two functions are inverses of each other. Okay. Now I can go ahead and test it in the other direction and see if that's so. So as you can see, that's my inverse. And I've just a little simplification. And whether or not I'm dealing with the positive case or dealing with the negative case, it's still going to come out to be a positive anyway. And there's my original function back. I'm sorry, there's my x that I was looking for. So there's my evidence back and forth. Is that cool? Boring? Agreed. Hey, it's a rehash of algebra 2. But now here's the fun one. What does that look like? The reciprocal of a function. What does that guy look like? Well, when is this undefined? When x equals 0? When f of x equals 0. So whatever the roots were on f, what do you think I'll see? You ready for this? Hmm. Weird. Kind of goofy, isn't it? So let's look at this for a minute, because there's some interesting stuff that we should know about and look at and identify. All right, what happens at the roots? You can see them. No, you don't need to. But, for example, right there, the, the purple is the inverse, is the reciprocal. Wherever 0 was, an asymptote now is. Now, let's point out some other features in here, too. When farther away, if I put 1 over a big number, the result is a small number. So whenever the green function gets big, the reciprocal gets small, right? Let's think about this slope. Slope of that function. Neighborhood. Hill. Okay. Look at what's happening. Here, if you look at my local minimum right there, I have a local maximum as well. These are ways that the inverse of something. If I give you a function, you can make a set of table. You make a table and deal with what you put import what's our where it go maximums and minimums and whatnot. When you get to next year, we're going to be exploring that. For simple things, you can kind of like look at that table and say, where does it start? Where is it increasing? Okay. Also, your calculator has a minimum and a maximum feature. Second calculate 3 gives you a minimum. And second calculate 4 gives you a maximum. Okay. All right. So inverses. Yeah, right? Okay. Let's see if I can get my scale a little bit better. Yeah. Take a look. Ladies, gentlemen. Better? Okay. No problem. Now, if we look at this, the smartboard isn't as nice as the large screens are, but you can see how we're flipping over the line y equals x. This guy doesn't. This function doesn't have any asymptotes. No, they're just. It's a polynomial that goes wild after that point. It just gets really big, blows up really fast. But some interesting points. Whenever, if you're lying on this point, on this diagonal line, y equals x, that means whatever value of x that you plug in, you get back out again. If I plug in 10, I get 10 out. So look at where the graph and its inverse meet. The graph and its inverse intersect. And you can see it even in some of these other. If you look closely, where these functions intersect each other, they all intersect on the line. Because effectively, it's acting like a mirror. And whenever it touches a mirror, its reflection touches it also. Right? So this is a way for you to find important points from time to time about your inverse if you needed to graph one. Right? You could draw your function, draw a line y equals x, and know that your values are all going to intersect. The function and its inverse are all going to intersect wherever that first curve touched that line. So, let's try this. Because guess what you guys are going to do? Yes. You guys just had a 5-day vacation, man. You should have been working on my 10 problems, but that's okay. All right. You guys are going to be given an assignment. I think you can get it done by Friday. Where did I put it? Oh, an extra. All right. So, take a minute. And actually, I'm going to go ahead and stop this episode of the Ronco Show. This episode has been brought to you by F inverse and the reciprocal of F, and the line y equals x.